Hello everyone. So today we're going to start talking about minimum spanning trees, which is going to be important for us for Project 4, which is going to be released tomorrow. So there's an example here of call centers across the US, or sorry, not call, data centers across the US, and the data centers are supporting the internet via high-speed connection. So suppose that we've found or developed a new technology for high-speed communications. We've got a new fiber optic. It's 100 times faster than anything else, and we want to start connecting these data centers. And our goal is to give as many people as possible higher speed connections to the internet, and we have to remember that laying these new cables between these data centers costs money. We may have to be laying them in existing service tunnels. We might have to be digging trenches and small tunnels underneath roadways and all kinds of things to lay these cables, so it's very expensive. When we do that, let's say we connect these two red data centers here, and you have to play along with me on color. So we connect those two data centers, and then we decide, we should connect this yellow one over here. Well, now, if I were to lay this purple cable from the yellow one to that bottom one, that would be a waste of money, at least for now, because there's lots of other data centers that have not been connected, and these three have already been connected. I've already got a connection from, say, A to B, that yellow one. Indirectly, I can go up to C and then over to B. So this cable is a waste of money. Until every one of these data centers is connected, that cable is a waste of money. Because even though there's no direct route from A to B, from A to C and C to B, is still using the new fast technology, and it's faster than the old, whatever the old connection was. Even if there used to be a connection directly from A to B, the two-hop connection, A to C, C to B, is faster than the old technology. So we don't want to have any cycles. We want to get all of these nodes connected. We don't want to have any cycles, and we'd like to have the minimum same amount of money spent laying these cables. So that will produce a tree. Since everybody's going to be connected, there's not going to be any cycles. That's a tree is what we want to produce, and we want that tree to be spanning. We want it to connect everybody at all of these sites, and more than that, we want the cost to be minimum. So that's where we get the term minimum spanning tree. It's the lowest cost way to get everyone connected without producing any cycles. So here's the minimum spanning tree problem. So I give you a graph of vertices and edges. You want to find a subgraph of that with the same vertices and a subset of the edges. And we're going to pick that subset of edges such that all of the vertices are pairwise connected, either directly or indirectly. So as long as they get connected, I'm okay with that, whether it's directly or indirectly. The other thing is we want to make the sum of all the edge weights in our subgraph T, the tree, minimal. So if there was a cycle, we would get rid of it. And so T stands for tree here. Since it's a graph without any cycles, it must be a tree. So we're going to look at here a way to do it. This one's actually easy to do visually, a little bit harder to code. So we're going to look at a couple of different ways to code this. This is not one of them, but it is an obvious way to do it, and also it would be a decent way to do this, say, on an exam problem, on a written exam. I can say, hey, let me cross this one out, let me cross that one out. Okay, so I've got I've got a graph, and I want to produce a minimum spanning tree. We got the definition of MST there. So we've got this graph, and all of the edges in the graph exist. It is completely connected, but it's got cycles. So what we want to do is start getting rid of edges that we don't need. So let's go from the highest weight edge to the lowest. I say, okay, hey, I've got this. Oh, wait, just 1 second. I'm going to give Sam here moderator privileges. Okay, there we go, Sam. Okay, so we take our highest weight edge is 120. If I delete the edge with weight 120, do I still have a cycle? Yeah, it looks like it does, so let's get rid of that 120. And now, instead of our total weight being 420, our total, whoops, went too far, our total weight is 300. Okay, we still have cycles, we still have edges that can be removed. Let's look at the highest cost edge. Highest cost edge is 100. If I cross out the edge 100, is it still connected? Yep, everybody's still connected in directly or indirectly. That's fine, so we can cross out that edge, and we go down to a total weight of 200. Okay, there's still cycles there. Let's remove the highest cost edge. Wait, I can't get rid of the 80 because that would make C unreachable or unconnected. So we can't get rid of that one. Okay, what about 60? 60 is the next highest cost edge. If I remove that one, everything is still connected. So I can get rid of that edge of cost 60. And now I'm left with a total cost of 140. Now we've got 4 vertices, so V is equal to 4, E is equal to 3. That's the definition of a tree, assuming everything is connected. So if everything is connected and I've got 3 edges, I must have a tree. So we're down to a tree. We can't remove anything else. Things will become disconnected. And since we've removed the highest cost that exists every time, it must be minimum. Okay, so what I want you to think about for a minute here, and I'm going to give you time, is how could we do a few proofs? Now, granted, proofs is not the thing we're going to give you on exams in 281, but it's good to think about it because it helps our deeper understanding of the problem. So what I want you to think about is, could you prove that a unique shortest edge must be included in every MST? What we mean by unique shortest is, like, let's say there's an edge of weight 1. There is no other edge with a weight 1. Every other edge has a weight higher than 1. So if the shortest edge is unique in its cost, prove that it must be in every MST. What about the second shortest edge? Can you prove the same for the second shortest? Let's put the word unique in here, unique. So if the second lowest cost edge has a unique cost, could we prove that that one has to be in there? And how? First good question is, how would we prove this? What proof strategy would we use? So what strategy would we use? I would suggest proof by contradiction. So take a minute, think about how we could prove by contradiction that the shortest edge must be included in the MST. Yep, Kevin just caught up to me. Okay, so think about how we would do that for this one. And if you're having trouble with things like AVL rotations, that would be a great thing to come to the one-on-many Profis hours. And granted, there's going to be people who mostly want to be asking questions about the project, which is due today, but I'm happy to answer questions about theory stuff in Profis hours. Okay, so I've got a slide here. So I've got my, what I suppose to be my minimum spanning tree over here, and let's say that we want to start by assuming that 20 is not in there. Okay, so let's start by proof by contradiction. We'll assume that the unique shortest edge is not in there. Well, now we've got a disconnected graph. We have to get it back to a connected state. We can't use that edge from A to B because we're trying to prove we don't need that one. So let's add this one. Okay, so we're back to a tree now. Everything is connected. We've got a spanning tree, but it's not minimum. So if it's not minimum, I should add a lower cost edge back in. All right, let's add this edge of weight 20 back in. Now I've got a cycle. When I've got a cycle, I'm allowed to remove an edge to get rid of the cycle. When I've got a cycle, what do? I choose the highest cost edge in the cycle. We've got to get rid of that 60. So now we've proved that 20 has to be in there. Okay, now I'm going to clear out the markings on this one, and we can repeat this for the second shortest edge. Okay, so let's assume that 40 does not need to be in there. We've got to get our graph back to connected because now we've got A and B are connected, C and D are connected, but they're not connected to each other. So since I've got a disconnected graph, I've got to make it connected. I can pick, I don't have to pick the edge 60, I can pick the edge 100. I can pick some other edge that makes this connected. Okay, there we go. We're back to a connected graph. It is a spanning tree, but it's not minimum. So I want to add in an edge. If I was building this up, I'd say, hey, let's add in an edge with a lower cost. Okay, well, the lowest cost edge that would make this connected is to add this 40 back in. Oh, now I've got a cycle. When I've got a cycle, I'm allowed to get rid of an edge. I choose to get rid of the highest cost edge. That's the 100. 40's got to be in there. Okay, now what about that third lowest cost edge? So let's clear our markings and go back. What about that third lowest cost edge? Well, let's assume that 60 must be in here. Okay, so I'm assuming that 60 must be in here. Wait, I've got a cycle. When I've got a cycle, I'm allowed to remove an edge. I choose to remove the edge with the highest cost that's part of the cycle. Oh wait, that's the 60. So the third lowest cost edge might be in there. It will be in there if it doesn't produce a cycle, but if it does produce a cycle, it won't be in there. With the first two edges, we didn't have to worry about it. When I pick 20 and I've got nothing else in my graph, I can't have a cycle yet. I pick a second edge can't produce a cycle, but the third edge could. So the third edge could produce a cycle. We don't include it. So we're gonna do an approach of how to solve this starting from the ground up in a few minutes. Okay, so here is a couple of simpler questions, no proofs. So what I want you to do is show me a graph with more than one MST. And what we mean by more than one MST means the same cost, different edges. So find a graph where you can pick different edges and still get a minimum spanning tree with the same cost. All right, so that's the first one. So figure out a graph that can do that. Show a graph and its MST that avoids some shortest edge. So if I had multiple edges with the same cost, show me a graph that would avoid one of those smallest cost edges, that has the same cost as some other edge. Okay, show me a graph where every longest edge must be in every MST, and that one's a little bit harder. All right, so take a minute, think about drawing these out. Not as easy to share these in our text box, I understand, but good practice for you before I show you answers. Okay, so we want to have a graph that has more than one MST. Well, we could do a really simple one. Let's just make a square. And if I say those edges all have a cost of 1, and then I've got 2 edges across the middle, we can even make this Euclidean true. So both of those edges in the middle have cost 1.414. Okay, so I want to make an MST out of this. Well, I could pick those 3 edges. I could pick those 3 edges. I could pick those 3 edges, or I could pick those 3 edges. So there's 4 different MSTs that all have the same cost. Now, this reminds me of something I wanted to mention is in Project 4. So in Project 4, I mentioned we're going to be implementing minimum spanning trees. In Project 4, unlike all the other projects, the judge, which is a program that decides whether your output is right, the judge is different from other projects. In other projects, you had to have the same output as us. In Project 4, each of the different parts has a different judge that says your output must be correct, even if it's different than ours. So here you could give one of 4 possible different MSTs and still get the right answer. You could also, for each of these, you could list the edges in a different order. I could list the edge, let's call these like A, B, C, D. So you could say, hey, I've got the edges A, D, D, C, and C, B. Or you could say I've got the edge B, C, the edge A, D, and the edge CD. So you can list them in different orders. In fact, there's 6 different orders for each of these. There's 24 different orders that you can list these in, and they're all right. So it's going to be able to, the judge is going to be able to indicate that any one of these is correct. So that makes it a little bit easier to get the right output. It just has to be an MST. It has to connect everything. It has to have the same cost as ours. It has to make sure your edges make sense. Like if you said, oh, I include the edge AC and I have a cost of 3, we'd say no, because that edge AC plus the other 2 edges doesn't add up to 3. It adds up to 3.414. You've lied to us about your cost. So it's just got to make sense. All right, so we've done number 1. We've shown a graph with more than one MST, and we've actually done number 2 also. Every one of these graphs avoids some shortest edge. There's a shortest edge avoided in each of these. Okay, so what about number 3? I've sort of filled up just about all my available white space on this one. Let's just clear out the upper right here since we're good with that, I think. Okay, so I want a graph that's got every longest edge must be in every MST. Well, what I could do is I don't have to have a really complicated graph. I just have to give you a tree. Every longest edge must be in the MST because every edge must be in the MST. So if I give you a tree to begin with, it is the minimum spanning tree because I've showed you these are the only edges that exist. You'd say, well, maybe I'd like the edge from A to C. Well, it doesn't exist. You can't pick it. All right, so what we're going to talk about for the rest of the day is 2 different algorithms named after the people who created them for creating minimum spanning trees. So these algorithms are intended to work on edge-weighted. So if the edges don't have weights, we don't need this complicated an algorithm. We just need to pick edges until it's connected. It's also intended for connected graphs, and it's intended for undirected graphs because we just want to get things connected. We don't want to have to worry about directionality. Now, if we have a disconnected graph, Kruskal can be, with a tiny modification, Kruskal can work on a disconnected graph, Prim's won't. Okay, the next thing about these two algorithms is they are greedy. And we've got a little bit of a chicken and egg problem here, is we've got a lecture coming up on algorithm families. And let me just check. So that's coming up tomorrow. But in order to really talk about algorithm families, we're going to need problems that are examples of different algorithm families. Also, just timing-wise, we'd like to get this lecture done before we hand you Project 4, because we're going to need this for Project 4. So what greedy means is we're always going to make the best choice that we can see right now that doesn't violate constraints. So what that means for MST is we would pick, say, the shortest edge I can right now that doesn't produce a cycle. Okay. And the other thing about greedy is we're never going to go back and redo a choice, or we're not going to change one of our earlier choices. So we're never going to go back and say, oh, wait, I made a bad choice a while ago, let's change that choice. That's not greedy. So greedy says we're going to make the best choice we can right now that doesn't violate constraints, and I'm just going to keep making those greedy choices. Now that's how a greedy algorithm works. For a greedy algorithm to be optimal, all of those best choice I can see right now has to produce the best overall set of choices that could be made. And it's possible to have a greedy algorithm that doesn't produce an optimal solution because those little greedy choices don't make a minimum solution. It happens to be that for MST, these two algorithms, the way they are greedy, does produce a minimum spanning tree. It is guaranteed. So Prim's algorithm is going to grow a tree from a single vertex. So we're going to start with a vertex, and we're going to grow our tree starting with that vertex. So we're going to connect something that is in our tree to something that's not in our MST. The Kruskal algorithm is going to grow a forest of trees that will eventually become one big tree when it's done. So you might have an edge over here, an edge over there, and eventually you're going to have a tree that connects all those vertices. Okay, so Prim's algorithm. Prim's algorithm says we're going to start with a single vertex chosen arbitrarily. So it doesn't matter which one we pick. So we're just going to make an easy choice and say this one is now part of our MST. Then what we're going to do is step 2 says we're going to grow the tree by one edge at a time. Of the edges that connect the tree that we have so far, to the vertices that aren't in the tree, we're going to find the minimum weight edge that connects the tree to not the tree. We're going to add that vertex and that edge, that corresponding edge to the tree, and then we're going to go back to step 2 until everybody's connected. Okay, so here's Prim's algorithm. We're given a graph of vertices and edges. Now, this is a description. This is going off of Prim's original description of his solution. It doesn't mean you have to implement it this way. We can implement it more simply if we don't worry about who are the innies and who are the outies in terms of, like, I don't want a set. I don't want a set that I have to then remove things from one set and insert them to another set, because that might take too long. So we have these ideas of the vertices that are in and the vertices that are out. The innies are initially empty. The outies are initially all the vertices. We're going to choose our first vertex to become part of the inset arbitrarily. We just pick one. And then we keep repeating until no one is in the outset. We say choose the outie with the smallest distance from any innie. We move that one to the innie. And then our implementation issue really is, how do I find this smallest distance? How do I find the one that's out who has the smallest distance to anyone in? We could use a linear search, which usually seems like a bad idea. We could use a priority queue. We could use a min heap, where the minimum value is at the top, and say, hey, let's pick that one at the top of the heap. And it's going to turn out that which one of these choices we use is going to depend on our graph. Okay, so Prims, one way to implement this, and the way that we're going to run through all the examples and the way that can be done for the project 4 and get all the points, is we're going to we have to record for every vertex. We've got to record 3 pieces of information. Now you could make 3 vectors, but this is a bad approach to things. Don't make 3 vectors each with 1 piece of data. Better yet is to have a vector that can, one vector that contains a class or a structure, and the class or the structure would have these 3 pieces of information in it. So for every vertex, we need to record its known status. Do we know the best way to get to this one yet? Initially, everybody's false. Next piece of information is the distance. What is the minimum edge weight if we were to add this vertex? What's the minimum cost way to add this vertex? Initially, that cost is infinity for everyone except the one that we choose to be the root starts out as 0. So the one that we choose to be the root of our tree has a distance of 0 from itself. Last thing is, what vertex precedes this one? Another way to think of it is, which vertex is this one connected to? Now, we need that one if we're going to tell you what the tree is. If we don't care about what the tree is, if we just care about the cost, we don't need P. But if we want to know, hey, you've got to connect this vertex to that vertex to get that low cost, we got to have P. Okay, so here's our basic algorithm. We're going to start out, like we said, everybody's false, everybody is infinity, and everybody does not know who their predecessor is. And we're going to change one thing. Before the loop starts, we're going to pick our starting vertex and set its distance to 0. Then, notice we're going to loop here. We're going to loop through these steps. Every time we've got to mark some vertex as true. Since there are v vertices, we've got to loop v times. So we're going to loop v times, and we're going to say, step 1. What I've got to do is, for all the false ones, find me the smallest false one. Remember, we've got a table of values. Step 1 also involves a loop. Whoops, L-O-O-P. We're going to have to loop over the table and find the smallest false one. Step 2 is just mark that one as true. Step 3 is going to be a loop also. Step 3 says, loop over your table, and for everybody that's false, see if we've found a better way to reach that vertex. So if someone in the table is false, does this new vertex that we found in step 1, does this new vertex give us a better way to reach some old vertices that we didn't know how to reach? Or if we did know how to reach them, does it give us a shorter cost way to reach them? So this is going to become a lot more clear when we run through the example. One thing about this, implementing this in Project 4, I'm going to see, even though I've added this slide for several semesters, I'm going to see people that ignore it and can't figure out why the heck their algorithm doesn't work. Notice here, it does not say, set the first vertex to true outside the loop. It does not say, set the vertex to true outside the loop. People are still going to do it, and they're going to get it wrong. The reason is, it seems like a really simple change, but that really simple change makes it really easy to get it wrong. So you should do what we said. Mark 1 to a distance of 0 outside the loop and run through the algorithm in the order listed. Okay, so here's our graph that we've given you. The numbers show us all the edges that exist in the graph. So there's no edge from B to E. That's okay. That edge doesn't exist in the graph. It has no cost. Or we could think of it as an infinity cost. So the cost from B to E is infinity. We would never, ever pick it. So we've got everybody is false. Everybody is infinity except for one vertex. I just said start with A. How did I arbitrarily choose A? It was the first thing in my vector. That's as arbitrary as anything else. It doesn't matter which one we pick. We will still get an MST. We just need to pick one to mark as a distance of 0. And the table really should say, hey, I don't know the predecessor for anybody. I don't know how anybody's connected in this MST. Okay, so let's run through the algorithm. Algorithm says, step 1, we've got to loop through and find the smallest false one. Now what we could do is we could start out and say, hey, what's my current vertex and what's my current distance? Right now my current distance is infinity because I don't know anything. Now let's go through the table and see if we can find something better than that. So I look at row A, or we could think of this as row 0. This V is not actually part of the vector. V would be our index into the vector. And in project 4, what we're going to do is all the vertex names are going to be numbers, like 0, 1, 2, 3, 4. So they're going to be, numbers are going to be in the range 0 to n. And so since we've got numbers in the range 0 to n, we can use them as indices. In the examples, if I use too many numbers, it gets confusing. Wait, is that a number or is that an edge weight? Is that a node number or an edge weight? So in the example, we're sticking to letters. So we go through every row and we say, hey, if you are false, is your distance better than my best so far? Aha, yes it is. So I've got a distance of 0 if my current vertex was A. And I keep going through. I check row B. Do you have a better distance than 0? No, 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 no. Okay, we've gone through all the false ones. We have finished step 1. We've checked all the false ones. We've found the best distance in the table. So now we go to step 2. Step 2 says mark this vertex as true. So this vertex is true. It's in the inset. And now we've got to do step 3. Step 3 says loop through the table. Oh wait, I didn't quite finish step 2. Step 2, I've also got to mark it as true in the table. Okay, so we've marked it as true. Step 3 says go through the table and look for anyone that has a false known value. And if its known value is false, figure out if we've found a better way to reach it using this current vertex. Okay, so let's go through everybody in the table. B, have I found a better way to get to B? Well, B used to have a cost of infinity, but now if I go starting at A to B gives me a cost of 13. That's better than infinity. So we update this distance to be 13, and we update the predecessor. If we choose later on to add vertex B at a cost of 13, how did we get there? Who is it connected to? It's connected to A. A because A is the current vertex. Okay, we got to keep going through the table. Vertex C, you've got a cost of infinity. You could get there from A to C at a cost of 8. 8's better than infinity, so we update the cost and we update the predecessor. D, we can get there at a cost of 1. That's way better than infinity with the predecessor of A. What about A to E? There is no edge from A to E. Infinity, is infinity better than infinity? No, so we don't update it. A to F, no edge, that's infinity. Is infinity better than infinity? No, we leave it alone. Okay, then we're going to change slides here. That's everything we just did in the first slide is now reflected in this one. That slide represented one time through the outer loop. We went through all of step 1, we did step 2, we did our loop for step 3. Now we go back through the outer loop. Remember, the outer loop says we got to loop v times. We got to loop v times because every time we're going to mark one more thing as true. Okay, so what's my current vertex? I don't know. What's my current distance? Infinity. Let's find the smallest false one. A is already true. We're not allowed to look at it. B is false. B has a distance of 13. That's better than infinity. That means B is my current vertex. Move on to C. C is a cost of 8. 8's better than 13. Well, now my current vertex, my best so far, my best false one so far is C. Move on to D. D is false, has a cost of 1. That's better than 8. So D is my best so far. Move on to E. Infinity. Not better than 1. Move on to F. F is false. Forgot that for step E. So for vertex E, it's false. Infinity is not better than 1. We move on. Vertex F is false, but infinity is not better than 1, so we don't change it. So we've finished step 1. We have found the smallest false one. Step 2, mark it as true. So step 2, I'm going to circle it up here, just visually to remind us, and we're going to mark it as true over there. Now, we've got to go to step 3. Step 3 is the loop that says, let's update the false neighbors of our new vertex D. So we've got to update the false neighbors of D. We look at A and we've got to go through the whole table. We look at A and we say, wait, A is already true. We can't change it. We've already found. Remember, K is telling us, I know the best way to reach A. We can't change A. So A is fine the way it is. B is false. Have we found a better way to get to B? Well, D to B is infinity. That's not better than 13. All right, what about C? C currently has a cost of 8. I can go from D to C at a cost of 5. 5's better than 8. So let's update that distance to be 5. And we've got to update the predecessor. It's not A anymore. It's our current vertex, D. So we've found a better way to reach C. We get there from D. Go to vertex D. D is already true. We can't change it. E. E is false. Have we found a better way to get to E? Well, E, currently we know how to get there at a cost of infinity. We could get there from D at a cost of 4. That's an improvement. So 4 and D is our predecessor. What about F? F is false, so we can look at it. F has a distance of infinity. D to F, a cost of 5, is better than infinity. So we change its distance to 5 and its predecessor to D. All right, that finished our step 3 loop. Go on to the next slide. So in here I've shown which vertices are in and which edges we have selected when we made those choices. Whoops, sorry, it went one too far. Okay, so the first time we got a vertex, this time we got a vertex and an edge that's in there. Okay, so we got to run through our algorithm again. Current, I don't know. Current distance, let's assume it's infinity. And let's find the smallest false one. So that's step 1. A is true, we can't look at it. B is false. B has a cost of 13. That's better than infinity. Okay, C is false. That's a cost of 5. So that's better than 13. Now, while we're at this point, I just want to take a moment to show you something about prims. Because you might say, hey, there's a 5. What if that 4 wasn't a 4? What if that was a 6? What if that was a 6? Would you pick C at a distance of 5 or F at a distance of 5? I would tend to pick C just because the second 5 wouldn't be better, but it doesn't matter. If I pick one of them, eventually you'll see I might pick the other one or I might not. It doesn't matter because I will end up with an equivalent MST no matter which one I pick. So you don't have to worry about this too much in implementing the algorithm. I would tend to say if the new distance is better than my current distance, then I make the change, otherwise I don't. But it really doesn't matter. If you say less than or equal to, you're still going to get the right answer. Okay, so let's get rid of those changes. All right, so we got to pick up where we left off. So we were at vertex C. We go to vertex D. D's already true. We can't look at it. Vertex E is false. E has a distance of 4. 4 is better than 5. So we update our best so far. Then we go to vertex F. F is false, but it's not an improvement, so we don't pick that one. All right, we've found our smallest false one. We finished step 1. Step 2, mark it as true. So I'm going to circle that one. Hey, let's draw in that edge. I picked that, and E has become true. All right, step 2 is done, marking E as true. Step 3, let's loop through all of the false edges, all of the false vertices, and see if we found a better way to reach them. Okay, so using E, we loop through here. A is already true, can't look at it. B, have I found a better way to get to B? No, E to B is infinity, can't improve it. How about C? I can now, if I go from E, I can reach C at a distance of 3. That's better than 5. So I change that to 3 and change that predecessor to E. All right, how about D? D is already true, we can't change it. E is already true, we can't change it. F, have we found a better way to get to F? F is false. F has a distance of 5, but we could go from E, the current vertex, to F at a cost of 2. That's an improvement if we use E as a predecessor. All right, we finished step 3. We've updated the neighbors. Now, we can fast forward this a little bit now that we're good at it. We can say, hey, step 1, I've got to find the smallest false one. B is okay, C is okay, F is better. So B is okay, C is better, F is better still, F is the one. So F is our current vertex. Let's mark it as true. And we just happen to pick that edge. We've got to now update the neighbors. So A is already true, can't do it. B, can't get to B from F. C, can't get to it from F. D is already true, E is already true, F is already true. There was no neighbors to update. So next slide. Okay, we got to loop through, find the smallest false one. So our current vertex is B at a distance of 13. Wait, C is better at a distance of 3. All the others are true. All right, C's our new vertex. Step 2, mark C as true. And remind ourselves we picked that edge. C gets marked as true. And now we update the neighbors. Well, A is already true. B, I found a way to get to B at a distance of 15, but that's not an improvement to the 13. Leave it alone. C is true, D is true, E is true, F is true. We're done updating neighbors. Next slide. Find the smallest false one. There's only one that's false at all, so it's got to be B. B becomes our new vertex. B gets marked as true. That's step 2. Step 3, update the neighbors. Everybody's true. We can't update anybody. We're done. So there's our graph and what it looks like. Now, when you write the program, you don't actually have a graph, but you've got the table. So we can go through the table and we could print out what are the edges that we selected. We could also, let's look at this. I know you don't have the Project 4 spec yet, but when you do this in Project 4, Part A, what you're going to do is you're going to print out the cost of the MST first. Where do I get the cost of the MST? Well, just sum up everything in that column. 13, 16, 17, 21, 23. So I'd say my total cost is 23, and now I've got to output the edges. Now, here's where picking the very first element of the vector as our first one to mark as true, or sorry, to mark as a distance of 0 comes in handy, because this one doesn't have an edge. This one doesn't have a predecessor. It's the root. So what I'm going to do to output the edges is, I'm not going to look at this one. I'm going to start here at index 1 of my vector. So at index 1, I've got, or really, let's do it in English first. Let's do it with our example. So in row B is connected to A. Now, the project requires you to list the vertices in order from smaller vertex to larger vertex. So I wouldn't say BA, I would say AB. Go to the next row. CE, that's in the right order. It's in increasing order of vertex name. Next one, DA, we would print AD. Next one, ED, we would print DE. And the next one, FE, we would print EF. And there's supposed to be a space between all of those. I know my DE doesn't quite look like there's a space in between them. Now really in your project, these wouldn't be letters, these would be numbers. So instead of AB, it would be 0, 1, 2, 4, 0, 3, 3, 4, 4, 5 would be our output. And this would actually have a 0.00 behind it. So that's what the output would look like for part A of project 4. So we look at what is the row. Remember, the row number is not in the vector. The row number is our loop variable. My loop variable compared to table sub. So if this was like I, if this is I look at I and table sub I dot P. And I print I and table sub I dot P, and I print them in increasing order, smaller one, bigger one. Okay, so that's how Prims works. What I want you to do is take a minute or two, do it yourself with this graph. It says start at node A. So node A is the one that's going to start out at a distance of 0. So you can start working on this. I'm going to make my Prims table. Remember, everybody is false infinity except A gets a distance equal to 0. But everybody's going to be false. Everybody else is going to have infinity as their distance. So start working on this. I'll start making the table, and then we'll run through it together. Okay, so we've got our table ready. I'll give you another minute or two to work on this. Okay, so you should be either close to done or at least got a pretty good idea of how this works so far. So let's run through this together. So we've got A is marked as distance of 0. So we do step 1. We find the smallest false one. So our current vertex is A. Current distance is 0. So then that was step 1. Find the smallest false one. Step 2, mark it as true. Step 3, loop through and update the neighbors. So when we loop through, we can sort of look at the table and the graph when we're doing this by hand. So I loop through, I say, okay, let's see, B is connected to A, distance of 1 is better than infinity, and I get there from A. C, I can get there at a distance of 3, that's better than infinity if I get there from A. D, I can't get there from A. E, I can't get there from A. So that's my step 3. That's our first time through the outer loop. Whoops, sorry. Went to the answer. I thought I had multiple slides here. We got to keep using this slide. Slight mistake on my part. Okay, so we've done the one vertex. We got to go back through the outer loop. So we got to find the smallest false one. So we start out here. I don't know a current vertex. I've got a best distance of infinity. Let's find the smallest false one. Okay, I've got B at a distance of 1 is better. And we only look at false ones. We don't look at A because it's true. B has a distance of 1. That's better than infinity. C is 3. That's not better. Or I should say C is false and 3 is not better. D is false, infinity is not better. E is false, infinity is not better. B is our best one from step 1. We found the smallest false one. Step 2, mark B as true. Okay, so now step 3, let's update the neighbors. Okay, so we go to C. Okay, so A and B are already true. C is false. We could get there at a distance of 4, but that's not better than 3, so we leave it alone. All right, how about D? D is false. I can get there at a distance of 6. That's better than infinity if I use B as my predecessor. E, I can get there now at a distance of 7. That's better than infinity, and it was false to begin with. So it's false. 7 is better than infinity if I use B to get there. Okay, we're done going through the outer loop. We got to go back to the top. Start by assuming I don't know a current vertex. My best distance so far is infinity. We check A is true, B is true, C is false. C is false. C has a distance of 3. That's better than infinity. So my predecessor might be vertex C. Vertex D is false, but 6 is not better. E is false, 7 is not better. So we've found our smallest false one. Step 1 is done. Step 2, mark it as true. All right. Step 3, update the neighbors. So we run through the vector. A is true, B is true, C is true. D is false. Have I found a better way to get to D? Well, I can go from C to D at a cost of 5. 5 is better than 6. So I would change my distance to 5 and my predecessor to C. The distance from C to E is infinity. E is false, but infinity is not better than 7, so we don't update that. All right, we finished step 3. We've updated the neighbors. So we go back through the outer loop. I don't know anything. Best distance so far is false. Let's find the smallest false one. Let's see. D at a distance of 5 is better than infinity, and D is false. A and B and C were true, so we ignore them. D is a distance of 5. E is false, but 7 is not better than 5, so we're done with step 1. Step 2, mark D as true. And then step 3, update the neighbors. Well, A, B, C, D are all true. E, I can get from D to E at a cost of 2. 2 is, and E is false. So E is false, I can get there at a distance of 2. 2 is better than 7 if I use D as a predecessor. Okay, I've finished step 3. Go back through the loop, outer loop. I say, hey, my best distance is infinity. Find the smallest false one is a distance of 2 is E. E is the smallest false one. Step 2, mark E as true. Step 3, update the neighbors. everybody's true, they can't be updated. We're done. So we've got our MST done. If we look through the table, we sum up the distance column, we get 1, 3, and that's 4, another 7 is 11. So we'd say, hey, I've got a cost of 11, and let's print out starting in not the first row, because the first row has no predecessor. There's no edge there. So starting at this row, let's print them out. So we've got AB. In this row, we've got AC, because we want to print them in order from smallest to largest within this row. Overall rows, we don't care. Let's go from top row to bottom row. But within a row, we got to list the vertex and the predecessor in increasing order. So DC, we would say CD. Go to the next row, DE. And that's what our output would basically look like. So this is our MST. That's what it looks like. That's what the graph looks like. But really, in Project 4, Part A, this is what our output would basically look like. Probably be a 0.00 there, and these would all be numbers like 0, 1, 0, 2, 2, 3, 3, 4. Okay, so let's look at complexity. So the complexity of this, and, okay, I didn't realize this when I posted the slides. It looks like I forgot to make sure that there were slide numbers on the slides. You can always refer to the page number, but I didn't realize that the numbers in the bottom corner were missing. Okay, so the complexity. So we've got a loop until every KV is true. Well, we know, we already said earlier, this outer loop is going to run V times. And this is assuming that we're doing what we just showed visually, the linear search. So assuming we're doing a linear search to find the smallest false one, so then we've got to do the linear search, we've got to say, hey, from the set of vertices for which KV is false, select the vertex D having the smallest tangent distance D. So we're going to run this outer loop V times. Step 1 is a loop that is O of V. We've got to run through the whole table, look at every one, see if it's false. If it's false, does it have a better distance than the best so far? Step 2 is O of 1. We just mark it as true. Step 3, we've got to run through that whole table, and we still have a constant amount of work for every row. So I've got to run through all V rows. I check if it's false. I check whether the distance to my new vertex V is better than what's in the table. If it is, I change what's in the table and I change the predecessor. So I change the distance, I change the predecessor. So I'm going to have to loop. So what it says by most at this vertex is I picked a vertex here. The most neighbors that I'll have to update is V of them. So that's what it means by most at this vertex. I've got to loop through everybody. I've got to update all the false ones, maybe. I've got to update all the false ones that now have a better distance. But the amount of work there is O of 1 for every one of those vertices. So I've basically got an outer loop. I've got an outer loop that's running V times inside of it. I've got a cost of V for step 1, plus 1 for step 2, plus V for step 3. So that should say, big theta basically of V squared. That's our cost. There's no best case, worst case, average case. This is always this amount of work. We've got to run through everything in the table, find the smallest false ones, etc. So we're going to get V squared work here if we do linear search. Now, what if we did it with heaps? What if we used a priority queue? All right, so here's running through the whole algorithm in each step. So we've got to initialize. We've got to figure out the number of vertices. That's easy. That's O of 1. I've got to create the table. Well, we sort of skipped that on the first one. We got to create the table. I've got to have a table that has a bunch of K's that are false, D's that are infinity, and P's that are whatever I use to say, hey, this one's not connected yet. So I've got to initialize all of those, and that takes O of V time, or O of N time. Okay, I've got to create an empty priority queue. I've got to mark the first vertex as a distance of 0, and I've got to insert something into the priority queue. I've got to insert, hey, vertex 0 has a distance of 0. Now, it says O of 1 here because I know I'm inserting into an empty heap. If I'm inserting into an empty heap, it's O of 1. All right, so what we're going to do is we're going to use priority queues to get this algorithm working. So here's what we do. So we say while the priority queue is not empty, I'm going to get the minimum out of there. That's a top and a pop. Now let's see. Oh wait, I forgot the complexity. So the outer loop is going to have to run E times because every edge is going to have to be put into the priority queue at some point. So to get that priority queue empty, I'm going to have to run E times. E is the number of edges in the original graph. So I've got to run E times, and then each step has a amount of work. So now getting the top and popping, really the top is O of 1. But popping is log E because I don't know. See, I'm in the middle of a loop that's running a lot of times. The very first time, yeah, it's going to be O1 for the very first one. But later on, as more things get added to that heap, binary heap, remember, if we don't say otherwise, we mean binary. We don't need pairing anymore. So I've got a binary heap. Popping that top one off is log of the size of the PQ. The size of the PQ can never be bigger than E. So I've got log E for that step. Then I've got to check if it's not known. That's an O of 1 cost to say, hey, do I already know this vertex? Now here's the reason why we need that step. If we look back here, okay. I got to find the right point. So at one point I had, here we go. Okay, so at one point F had a distance of 5. I discovered that, and I would have added that to the PQ. So my PQ, my priority queue, my binary heap, would have, one of the things in it would have been F at a distance of 5, would have been in there. But then later, when I discover that I can go from E to F at a distance of 2, I would also add to the priority queue F at a distance of 2. F at a distance of 2 would come out of the priority queue first, and I would mark F as true. Then later on, F at a distance of 5 would come out of the priority queue, and I'd say, oh, this is outdated information because F is already true. I don't need this one anymore. So I don't need to look at this one because it's telling me about a vertex that I've already found a better way to get to. But F at 5 went into the PQ, F at 2 went into the PQ, F at 2 came out first, F at 5 comes out later. So that's why there's this if. And this is the end of the while loop, basically. The end of the while loop, we could think of it as down here. So this if statement is, if we don't know it, we do work. But if we do know it, what's going to happen is we're just going to go back through the loop and grab something else. So F at a distance of 5. Hey, I already know how to get to F. Throw it away. Let's go back through the loop, get another minimum off the top of the PQ. Okay, so if it's not known, checking if it's known was an O of 1 check. Next step, mark it as true. O of 1. We just got to mark it in the table as a true value. Then we've got to run a loop. We've got to run a loop for every vertex in the adjacency list. That's what that means. In adjacency of V0 means in the adjacency list. Well, we know that the cost to run through an entire adjacency list is 1 plus E over V. So we've got 1 plus E over V is how much work we've got to do here. And then we've got to, so this is another for loop inside of the while loop. So this for loop is going to do some stuff. It's going to do update the distance, or actually, sorry, calculate the distance. I calculate the new distance. That's O of 1 to calculate it. I check if it's better than what's in the table. That's an O of 1 check. If it's a better distance, we update the distance in the table. That's O of 1. We update the predecessor in the table. That's O of 1. And we insert into the priority queue. Inserting into the priority queue is O of log E. Now, we got a problem here because we're inside of a loop that's inside of a loop. But there's a saving grace here. Because we can never visit an edge more than once, this whole thing here, this whole for loop, even though it's inside of a while loop, think about the total amount of work done by this loop. We are never going to look at an edge more than once. Really, well, we'll look at it twice. We'll look at an edge twice, but because it would be E, O of E. So we're going to loop through all E edges. We're going to loop through all of the edges, and we're going to check if we've found a better way to get to it. So we're going to run through, this loop is going to run through a total amount of work, even though it's inside of the outer loop. This loop will never run through more than O of E stuff. It looks at all the edges. O of E times log E. So really we've got, if we think about it, let's calculate the complexity a little bit differently than last time. Let's think of the complexity of all this stuff and the complexity of this thing total. Well, this one is E times log E. And this one down here, let's just do it in a different color, this one is going to run, it's going to run through every edge. For every edge, it might do a push of log E. So I've got E times log E plus E times log E. That's my complexity for this loop. It's E times log E is my total amount of work in this whole big while loop. Yes, the PQ contains pairs. That's what we showed right here, is we say insert a distance vertex pair, because the distance controls the priority, but when I need to know the vertex when it comes out, which vertex should I mark as true? Okay, so then if we look at Prim's overall complexity, if I use the nested loop implementation with the linear searches, this is when we said with linear searches, we get O of V squared. If we use the priority queue, we get O of E log E. But let's think about this. O of E log E, we said we were going to use an adjacency list. The adjacency list assumes we've got a sparse graph. If we were to do this with a sparse graph, oops, can't type. Okay, so if we were to do this with a sparse graph versus a dense graph, in a sparse graph, E is proportional to V. That means we've got O of V log V. Here, in a dense graph, E is proportional to V squared, which means we've got O of V squared log V squared, which is the same as O of V squared log V, because remember the power rule, if we've got log of V squared, that's equivalent to 2 times log V, or actually with big O. Or actually no, it's 2 log V. So we can take that exponent, we've got O of V squared log V. Oh, look at that. If we do the priority queue version with a dense graph, we end up worse than if we had just used the nested loops. So it's important that we do the nested loop version if we've got a dense graph. If we do the priority queue on a dense graph, it comes out worse complexity than if we had just gone straight to the loops. Okay, Kruskal's algorithm. So we finished one of our two algorithms today. Kruskal's is going to go a bit faster, especially on the example. So Kruskal's, another greedy algorithm. It's going to take one step. It's going to say, I've got to pre-sort the edges. That's O of E log E, which we know is proportional to E log V. So E log E, we got to sort the edges. And then what we're going to do is we're going to try to insert the edges in increasing weight. If that edge would produce a cycle, though, we can't keep it. So because we might pick the first two edges might not connect, that's why we say it's a forest, because I've got some branches over here, I've got some branches over there. Eventually they grow together into one big tree. So let's look at an example of Kruskal. So here's my graph. Now I could go through and sort the weights like visually. I could say, okay, AD is a distance of 1, EF is a distance of 2, CE is a distance of 3, and that takes a while to do. And I don't have that on every slide. So what we're going to do is we're going to do it visually. We're just going to be careful. We're not going to pick a longer edge when there's a shorter edge that we could have picked. All right, so we start out. Kruskal's algorithm, you aren't told a starting point. Your starting point is the shortest edge. So I'm going to pick this edge. So when I pick that edge, I've effectively connected those two vertices. So now, what do we do next? Next smallest edge, looks like 2. Let's pick that one. So I pick that edge. That's what my graph looks like now. And I put them in a different color because they are separate regions. They are separate trees in the forest. Okay, anybody else length 2? No, I got a length 3. Let's pick that length 3. It now looks like that. And also, one thing we should have been doing, starting with the third edge, see, 2 edges can't produce a cycle. 3 is the shortest edge and it doesn't produce a cycle, so we can pick that edge. Okay, how about any 4s? Yep, we've got 4. If I pick that edge, does it produce a cycle? No. Not only does 4 not produce a cycle, it joins those two regions into one region. Okay, edge of length 5. I've got 2 of them. Does it matter which order I check them in? No, because neither of them's in. If it did matter, if one of them could be picked and the other couldn't, it's still, the order doesn't matter because I'm still going to get an equivalent MST with the same weight, just a different choice of edges. So I check one of them. Can I pick this one? No, it produces a cycle. This one? No, it produces a cycle. How about 5, 6, 7, 8? Oh, how about 8? No, it produces a cycle. 9, 10, 11, 12, 13. How about 13? Aha, 13. Does it produce a cycle? No, it gets me B connected. All right, how about 15? We said let's sort the edges and check every edge. How about 15? Oh, wait, no, it produces a cycle. We can't keep 15. That's our graph. So visually, Kruskal's is really easy to do as long as we don't make a mistake and like pick the 5 before the 4. We can do this visually really easy. So the complexity of Kruskal's, the sorting takes E log V, or remember we said this is equivalent to E log E. So really, if I've got E edges, it takes E log E time. But remember, E is either proportional to V or E is proportional to V squared. Either way, it's log of V. It just so happens that the sorting is the most expensive step of this algorithm. Now, what we're going to have to do is when we loop, we're going to loop. We've got to run the loop E times. We've got to loop over every edge. We've got to say, so it says discarding an edge is trivial and adding an edge is easy also. Think of it as adding an edge is what I'm going to do is I'm going to like push the edge into a vector. And I even know how big the vector should be up front. If I've got a connected graph, there better be v minus 1 edges, so I can reserve the vector up front to be size v minus 1. So pushing into the vector is O of 1. Discarding means I don't push it into the vector. I just do nothing. So discarding an edge is easy. I don't push it to my vector of which edges I kept. Adding an edge to that vector is O of 1. Most of my time is spent searching for cycles, as long as it takes less than log e time, because remember, this loop is going to run e times. I got to loop through every edge. As long as checking for cycles and preventing cycles takes less than log e time, then the sorting is the bulk of our time. So I want to know, can I connect vertex I and vertex j? Well, if they're already connected, we can't connect them. How do we do that? We need to do the union find. So union find that we introduced earlier when we were talking about, what was it, containers or sets or something like that, I forget which lecture. When we did it before, we didn't have an algorithm that needed it, but it was a cool thing to talk about and was related to our earlier topic. But now we've got a reason we need it, is I don't want to duplicate effort. I don't want to connect them with roads or train tracks on Mars or fiber optic cables buried in the ground that are expensive to bury. I don't want to lay those cables if I would connect two that are already connected. So we're going to do this representatives. Everybody has a representative of their group. We do the union and find operations. Find tells me who is your representative. Union says, well, if I do a find on each and they have different representatives, then I can put them together into one. And we're going to start. This is where we started. Remember, we said we're going to have n disjoint elements. To produce an MST, I need one region with everybody in that one set. And so we're going to do the, remember, we don't have to know our representative as long as we know someone who knows someone. So we're going to know someone who knows someone, and if you ever find that you don't know who your representative is, we're going to update it so that you really do know the ultimate representative. So if like 4 says 3, and 3 says 2, and 2 says 1, and 1 says 0, what we're going to do is when we ask, we do a find on 4. We go all the way through and we find 0, and 0 says me. I'm the ultimate representative. Well, then what we're going to do in path compression is, as we go backwards through our unrolling our recursion, we're going to say, hey, 1, your representative is 0. 2, your representative is 0. 3, your representative is 0. 4, your representative is 0. So we update those representatives, and now we have compressed the path to one off of the ultimate representative. So now in the future, if I ask 4 says 0, 0 says 0, I'm done. We've got a constant length to most paths. And we said the total complexity to go from all disjoint up to one superset was n times alpha of n, which means the cost of one, the cost of doing one union is alpha of n. So going back to our complexity here, so does checking for a cycle take less than log e time? Yes, it takes alpha of v time, because v is the number of vertices that can be connected or not connected. So the amount of time here is actually alpha of v, and remember we said alpha of v is very, very rare to see an alpha of v that's higher than like 3 or 4. So it's effectively a constant. So our amount of work looping and checking for cycles and connecting everyone is basically, this whole loop is going to run e times, we said. So we've got e times alpha of v, which is almost, it's not quite, but it's almost equal to E times 5. Because alpha is very, very, very rarely going to be longer than that. And once it is, even if it happens once, we will compress that path length down to get it shorter so that it won't happen again anytime soon. So that's what we do with the path compression. Remember, this alpha of n is the inverse Ackermann function. Alpha of n looks like this. You say, what's the inverse Ackermann of 100 quadrillion? 4. What's the inverse Ackermann of the number of particles in the known universe? 4. So we're very, very rarely going to see an inverse Ackermann that's higher than 4. Okay, so here what we've got is a data structure. We got a graph. It says MST this. So we've got a graph. You can do this without worrying about the representatives. But we're going to run through the example with it. Now, to give you a starting point, just in case, I sorted all of the edges. I made everybody their own representative. So take a few minutes to run through this, and then we'll do it together. Okay, let's look at this example. So we've got our sorted list of edges. So we choose the edge AB. Now we know from the proof that we did earlier that the first two edges can't produce a cycle, but we still need to update our union find data structure. So I choose the edge AB. A says A, B says B. Yes, they have different representatives. Yes, they can be unioned. And in the union find data structure, I always chose to update the second one you asked about. So since the edge was listed as AB, that's the order I check them, and I always update the second one just to make it convenient in my code. So B would now say my representative is A. Okay, so we've got this in, I've got sort of a bunch of slides here, so we check this edge. We find they have different representatives. We can pick that edge, sort of the dotted line that there says we're thinking about it. So then we pick it and we change its representative. All right, so now we think about the next edge, which is DE. D says D, E says E. They do have different representatives, so we can pick that edge and we update E's representative to be D. All right, so next edge we think about, the edge of length 3, AC. A says A, C says C. They have different representatives, and so we can choose that edge, and C will change its representative to be A. All right, now we consider the edge BC. B says A, but we don't stop there with the union. B says A and A says A, that's when we stop the find. So B's representative really is A. We do a find on C. C says A says A really is C's representative. They have the same representative, so they cannot be unioned. We cannot pick that edge. So we discard that edge and move on. What about this edge? What about the edge from C to D? We check their representatives. C says A says A, that is the ultimate representative. D says D, we stop there. When someone says me, we're done looking. So C and D have different representatives, so they can be unioned. D is going to change its representative to be the same as C's. So we say D's representative really is A now, because I know C is going to tell me A. I change D's representative to A. Okay, so now we look at the edge BD. Now, depending on how we wrote our code, if we did a loop that said, I've got a loop over every edge, we would keep going. If we had kept track of, like, hey, every time I put one of these, like my tree, if I had a vector of vertices, if I pushed AB in there and I pushed DE in there, I pushed AC in there, and I pushed CD in there, I could stop when the size of this vector is equal to v minus 1. But let's pretend that we loop until we've checked all the edges, just 1, so that we can see what happens with representatives, and 2. If you loop until you get v minus 1, it doesn't work with a disconnected graph. But if we check every edge, Kruskal will actually work with a disconnected graph, and it'll give you a correct total weight. But the total weight would be the total weight for connecting this region, the total weight for connecting that region, and there was no way to connect the two regions, but you still have, you don't really have a minimum spanning tree, you sort of have a minimum spanning forest. So if we just loop until we've checked every edge, we won't have an infinite loop, and we'll stop when we're done. And we also get to see what happens here with path compression. So we check the edge BD. So we check their representatives. B says A says A, D says A says A, B and D have the same representative, they cannot be unioned. Now let's check this last edge, BE. B says A says A. When we ask E, who's your representative, E says D says A says A, so we know the ultimate representative is A, and we have to path compress. E has to say, my representative is now A as part of the find operation. The find operation changes that. Then we look and we say, oh, well, B and E have the same representative, we can't pick that edge, but we did perform the path compression along the way before we said, no, we can't pick that edge. And there's our final graph with the edges we've chosen. Now, we've got just 1 or 2 more slides here. So MST is this lowest cost subgraph that includes all the vertices or nodes and keeps them connected, assuming they were connected to begin with. Prims cannot work on a disconnected graph. Even with modifications, it would be hard to get it working. It could be done, but Kruskal is really easy to do. So we got 2 algorithms, Prim and Kruskal. They are both greedy. They're both greedy in different ways. And if we look at implementing these, if you've got a dense graph, we use the nested loop prims, or the nested loop prims, because it's O of V squared. The priority queue version of Prim is E log E. So if I've got a dense graph, nested Prim is O of V squared. PQ Prim would be O of E log E, which is the same as O of V squared log V squared. Kruskal is O of E log E, which in a dense graph is the same as that. So if the graph is dense, you've got to do nested loop prims. If the graph is sparse, it turns out that Kruskal is faster. In theory, they are the same. They are both E log E. But in the implementation, we've had multiple staff people implement this. And everyone who's implemented this, including people who went to like the world finals of the International Computer Programming Championship or Challenge or whatever it's called, the ACM programming contest, even people on those teams have never been able to produce a better priority queue Prim than their first version of Kruskal. So as long as you do your union find right, Kruskal is going to be faster. Theoretically, they're the same, but in runtime implementation, Kruskal comes out better. Last thing, which we're not going to ask you on the exam to do a proof, but if you want to just help your understanding a little bit, prove to yourself that Kruskal does find an MST. Prove to yourself that Prim really does find an MST. Another thing to think about is prove that it never produces a cycle. Kruskal, it's easy to see how it doesn't produce a cycle. Why is it that Prim never produces a cycle? Think about Prim starting at a different vertex. Do you still get the same cost of MST? You might get different edges chosen, but you will get the same cost. Do you believe that? And if you look back at the MST quiz, and proof by contradiction might be a way to do this. So we'll see you in office hours after lunch, and we'll get the Project 4 posted like super late tonight / early tomorrow, probably sometime past midnight. I'll make the Project 4 visible so that you can look at it a little bit before office hours tomorrow. And oh yes, one other thing, there is a video for Project 4. Video is already made, so that will be available right at the beginning.